Thank you to the organizing committee for inviting me, and my sincere apologies for not being there. I would much rather be in Paris with you than in Baltimore. We are going to be focusing now on interstellar objects, which will be the small end of the free-floating population. Although, given the many orders of magnitude difference in size, it's not clear that they are part of the same population, right? So interstellar objects are fairly new phenomenon. This image here was just taken a couple of weeks ago and shows HST observations of the third interstellar object that has been discovered just this last July. But before we talk about interstellar objects, let's talk about the broader context that explains why these objects are so exciting. Uh, so planetary systems are formed in protoplanetary disks. These disks contain about 1% of the mass of the central star. This initial phase sets the stage for all subsequent processes, and there are many unknowns. For example, the total amount of gas and solids in the protoplanetary disk, the size distribution of the solids, the disk radial and vertical structure, and the evolution of the disk itself. So these are snapshots from a numerical simulation that studies the growth of solids in a protoplanetary disks. And here you can see the disk from above the plane, and the growth of the solids is very efficient from dust particles with an initial size of the order of 0.5, 0.1 micron to particles of the size of a pebble. This is because the dust particles generally move with the gas flow, and therefore the relative velocities and collisional energies are small. And this, combined with macroscopic forces like van der Waals and electromagnetic forces, result in very efficient growth, as the particles collide gently with each other. So these particles eventually grow into kilometer-sized planetesimals, shown at the bottom of the figure, that through collisions and gravitational interactions can grow into larger bodies like asteroids, comets, planets. So planetesimals are the building blocks of planets, and understanding them is critical to understand planet formation. Planetesimals also play a key role in habitability, because collisions between planetesimals and terrestrial planets are a hazard, but also they are a source of life, because these planetesimals can provide water and other volatiles to the terrestrial planets, and as such, they can play a fundamental role for the conditions of life to emerge. And planetesimals also play a very important role in the dynamical evolution of the planetary system, because the disk of planetesimals interacts with the planets and can make them migrate. And as they migrate, they can eject planetesimals into interstellar space. What happened in the solar system, right? These are results from the NIST model. And we think, and here you can see the orbits of the giant planets, and they migrated, and this led to a readjustment of the orbits and to the ejection of a large fraction of planetesimals in the disk, leaving behind the asteroid and the Kuiper belt and the Oort cloud, right? So evidence that planetesimal belts in the young solar system were much more massive in the past and were cleared away by dynamical instabilities are the large number of craters in the terrestrial planets and the moon that correspond to an impact rate that is 4 orders of magnitude larger than in the Earth today, and also the presence of large Kuiper belt objects larger than 200 kilometers that require a more massive planetesimal belt for their formation via pairwise accretion. It is also thought that the Oort cloud, which we know it exists because it's the source of the long period comets, was formed by the ejection of planetesimals from the giant planet region into these very distant orbits with semi-major axis between 3,000 and 100,000 AU. In this case, the planetesimals were not entirely ejected, but remained barely bound to the sun as their pairs were lifted to prevent further ejection. So we have therefore evidence that planetesimals were ejected from the solar system when it was young, and we will see now that there is also evidence that these planetesimal ejections are common in other planetary systems. We cannot observe planetesimals in other planetary systems, obviously, but we infer they exist because of the presence of debris disks around many stars that form from the dust that is produced as the planetesimals collide and sublimate. This is a real image of the debris disk around Fomalhaut, taken with JWST. It's so beautiful that it looks like a simulation, but it's a real image. These are some of the questions that the British study are trying to address, because the dust traces the dust producing planetesimals. So we are trying to learn, is there evidence that planetesimals have formed in these systems, and where are they located? Does the morphology of the dust disk indicate that planetary mass bodies might be present and are responsible for shaping the disks via gravitational perturbations? If there are known exoplanets in these systems, where are the planetesimal disks located with respect to the planets, and are they interacting dynamically, and what can we learn about the overall architecture, dynamics, and evolution of the planetary system? And what can we learn about the composition of the planetesimals? And if they are located beyond the snow line, could they be sources of water and other volatile in the terrestrial planet region? And is there evidence of such volatile delivery? So one of the key aspects that we have found from the study of the British surveys is that planetesimal formation is a robust process that can take place under a wide range of conditions. And we have learned this from the extensive British surveys carried out with Spitzer and Herschel. Many of the debris observed as part of these surveys are not especially resolved, so we cannot see the disk, but we can study their spectral energy distribution. And that can shed light on the location of the dust once you extract the emission from the central star. So at 24 microns, the observations are sensitive to dust at approximately 150 Kelvin, that for a solar type star would be the temperature of dust particles located between 3 and 5 astronomical units, similar to the asteroid belt. And this is what we call warm dust. In the terrestrial planet Sun, the dust will be around 300 Kelvin for a solar type star. And this is also considered warm dust. And at 70 microns, the observations and beyond, the observations are sensitive to dust around 50 K. And that corresponds to a distance of approximately that of the Kuiper belt, 30 AU. And this is what we call cold dust. And this is an example of a spectral energy distribution down here that has a cold disk. So, and the histograms that you see here show how frequently we find debris emission. This is evidence of planetesimals around different types of stars. It's important to note that these surveys are limited by sensitivity. At 24 microns, we are only able to detect warm dust in systems that contain more than 100 times the amount of warm dust in the solar system, while at 70 and 100 microns that were observed by Spitzer and Herschel, the detection limit is between 10 and 20 times the amount of dust in the solar system. In both cases, we find that planetesimal disks exist around stars with stellar luminosities that differ by several orders of magnitude difference, and we also have find debris around stars with a wide range of metallicities. And from all of this, what we learn is that planetesimal formation is a robust process that can take place under a wide range of conditions. We also find that the dust-producing planetesimals that are located closer to the stars, so that will be what we observe at 24 microns, at shorter wavelengths, those planetesimals disappear fairly quickly. This is the comparison between the frequency of debris around young stars and around all stars, of the frequency of warm dust. So this is, again, tracing planetesimals in the inner region of the system. And they disappear quite quickly, but there is not much evolution on the outer system. And one of the reasons why this is the case is because the dynamical timescales in the inner region of the disk are shorter, and this makes planetesimal collide more frequently and erode more rapidly, causing the warm dust to decay as 1 over T, as you can see in these plots here. And in fact, the size distribution of the asteroids and the Kuiper belt objects are a fingerprint that this collisional activity played an important role in the early solar system history. But the other mechanism that is responsible for the depletion of planetesimals and dust in the inner region is the ejection of planetesimals due to gravitational scattering with planets. And we think this happened in the early solar system, and numerical simulations like these beautiful ones by Sean Raymond show that these episodes of dynamical stability and planetary system ejection are common under many planetary configurations. as you can see in this simulation here, where you have 3 giant planets and 2 planetesimal belts, an inner belt and an outer belt. And in these simulations, we follow how planetesimals grow and how much dust is being produced. So the point here is that planetesimals are common. We know that from debris disks, and we think that dynamical ejection is common. So this is a source of interstellar objects. ALMA has contributed spectacularly to the study of debris disk morphology. These are results from the recent ALMA program led by Luca Matra. They observed 74 debris in the millimeter and submillimeter. The bars here correspond to 50 AU. You can hardly see them here, but these are basically exo-Kuiper belts. And the disks, what I want you to notice here is that the disks show a very wide range of structural features, including narrow rings, extended disks, multiple rings. Some of them are eccentric. Some of these features may be due to the presence of planets. Some may be due to the interaction of the dust with the gas that is still present. And the radial structure of these exo-Kuiper belts is extremely diverse, showing a very wide range of radial extents, much wider than protoplanetary disks. So protoplanetary disks will be here in orange, and Kuiper belts will be here in blue. So it is certain that some of these dynamical paths will have contributed to the population of planetesimals in interstellar space, because there is a lot of structure. It is still not known how this diversity originates and how it evolved from the structure seen in the protoplanetary disk to the debris disk, to the exo-Kuiper belt. But it's almost certain that this would have led to the ejection of planetesimals into interstellar space. And that's the topic of what I want to discuss here. Another source of interstellar planetesimals are the Oort clouds. We don't have evidence that other stars are surrounded by clouds of loosely bound objects, but it's reasonable to assume that some do, given how prevalent planetesimal ejection is. So let's assume that Oort clouds are common and that the number of objects scales with the stellar mass and that their extent scales also with the Hill radius. So when a star reaches the end of its lifetime, it loses mass, and as a result, the objects in its exo-Oort cloud, because they would be weakly bound to the star, can be released into the interstellar medium. Planetesimals in the exo-Oort clouds could also be released due to close encounters with other stars or due to the galactic tide. These results here are by Dimitri Beras, and they show that bodies orbiting 1 to 8 solar masses beyond the boundaries seen in this plot would be subject to become dynamically unstable under the influence of post-main sequence mass loss here in the black lines. So the objects that will have periods beyond these lines here would be subject to become unstable, or due to the galactic tide, that will be the brown line here, or due to stellar encounters, that will be the pink lines here. Being dynamically stable doesn't guarantee ejection, because collision with the star is also possible. So the process dominating exo-Oort clouds would be stellar encounters for the stars that they are still in the main sequence, because we see that the boundary here is lower at lower periods. But for stars that are already leaving the main sequence, for post-main sequence stars, the main process for ejection will be the post-main sequence mass loss. That will be between 1 and 8 solar masses. For stars that are less massive than that, even though they lose half of their mass in their post-main sequence states, this mass loss is not strong enough to eject bodies from the exo-Oort clouds. That's based on studies by Veras et al. And for stars that are more massive, even though the sudden mass loss experienced during the supernova explosion would also trigger the ejection of exo-Oort clouds, it is uncertain whether these stars, these very massive stars, will actually harbor exo-Oort clouds because of the timescale for formation of these clouds. This table here, it has a lot of numbers, but I only want you to focus maybe on this percentage here in parentheses. These tables list the inner and outer radius of the XOR clouds for stars in the 1 to 8 solar mass range at 3 different galactocentric distances. And given this assumed radial extents, the table lists semi-major axes beyond which the objects would be subject to become dynamically stable. And in parentheses is the fraction of the or clouds that lie within the corresponding regime of influence. The bottom line here is that a large majority of the XOR clouds will be affected by these processes that can make the orbits unstable. So all this to say that planetesimals can also be ejected from the Oort clouds. So so planetesimals can be ejected from young planetary systems in the making or from XOR clouds of stars at the end of their lifetime. And this will contribute to the population of interstellar objects that in the deep freeze of the interstellar medium are expected to remain pristine, like time capsules of their planetary system more distant past. With all those planetesimals in interstellar space, it was expected that sooner or later the trajectory of one of them would cross paths with the solar system, becoming an interstellar interloper. In fact, before the detection of the first interstellar objects, we were actually puzzled that we had not detected any. So we look into this, making an order of magnitude estimate of the number density of interstellar planetesimals that could have been ejected during planetary system formation. And we found that this number density was low enough that the detection of these interstellar interlopers will require deep surveys and large discovery volumes like that of the Vera Rubin Observatory. So Oumuamua, the first interstellar object discovered, was not an unexpected visitor. It was very much expected, but in a way it arrived too early. It was discovered by Pan-STARRS, 1.8 meter telescopes, way smaller than Vera Rubin, and it was quickly identified as interstellar because of its clear hyperbolic trajectory, unlike any other solar system object. The eccentricity is almost 1.2. So it became remarkably close to the Earth, about 0.4 AU, that's 60 times the distance to the Moon. But unfortunately, by the time it was discovered, we were already here. So it was already on its way out, and it was only visible by ground-based observatories for another 2.5 months. Based on its brightness and distance, it was estimated to be about 100 meters across. So we were really lucky. The only reason we were able to detect such a small object, only 100 meters across, is because it happened to pass very close to the Earth. The opportunities that open with these first detections are really mind-blowing. Objects of this kind, as I said, could be planetesimals ejected from other planetary systems. So this is like having an interstellar return mission for free. So it's just mind-blowing. But as I said, its discovery pointed out to a tension with our expectations regarding the number density of these objects, because we didn't expect to detect one within the discovery volume provided by Pan-STARRS. So Oumuamua passed within 0.4 AU of the Earth. We also know that the Pan-STARRS survey had only been in operation for a few years. Though et al. Did very detailed calculations to calculate the number density of planetesimals based on Oumuamua's discovery, and found that within the orbit of Neptune, we would expect to have around 10,000 interstellar objects like Oumuamua. Remember, these are objects larger than 100 meters. That will be within a sphere of about 30 AU in radius. And regarding the expectations, we can calculate the number of interstellar planetesimals per unit volume of space based on the observed number of stars per unit volume that will be given here. So this calculation is for single stars and for white binaries. So this will be the number density of stars per unit volume, and then making some estimates about how much solids are in the system and what is the probability of ejection. So doing this type of, and we can do the same for XOR clouds. So doing this type of population studies that have a lot of uncertainties, so this is like, rough order of magnitude estimates, A generous upper limit to the number of objects that we will expect to find within the orbit of Neptune will be 2 orders of magnitude lower, around 100 objects. And this discrepancy points out that we still have a lot to learn about the population of interstellar planetesimals and their origin, in particular the size distribution, upon which these estimates are strongly dependent. In these calculations, we adopted a range of size distributions based on solar system observations of the small body population and also based on accretion and collisional models. But as I said, there are a lot of uncertainties, and until we have more information about the size distribution of these objects, we cannot really make reliable estimates on the number density. It could also be the case, because all these estimates, the estimate of the number of objects that are inferred to exist from the detection of Oumuamua is based on the assumption that Oumuamua is representative of an isotropic distribution of interstellar planetesimals. This will be the case, for example, if it is coming, but it may not. It may not be representative. And this may be the case if it is coming from a nearby system, in which case it may not have enough time for the distribution of those objects ejected into space to have become isotropically distributed. So, and in fact, a recent ejection from a nearby, and if it is not representative of an isotropic distribution, then the numbers that we will infer for the overall population wouldn't be that large. And in fact, there is evidence that Oumuamua may be coming from a nearby association because it was moving very close to the velocity of the stars in the local neighborhood. And this means that it had not been traveling for too long, because otherwise its velocity dispersion would be higher, as the velocities tend to increase with time as the objects encounter stars and molecular clouds. A recent ejection is also consistent with the fact that the surface of Oumuamua didn't seem to be heavily processed based on its color. KBOs, for example, Kuiper objects, are ultra-red because of billions of years of exposure to cosmic ray, plasma and radiation that process the surface, but Oumuamua's surface was not ultra-red, so maybe it was a young object. And another surprising aspect of Oumuamua was its morphology. This object, that was about 100 meters in size, had a brightness that fluctuated very sharply every 8 hours. Some brightness variation is expected because small rocky objects have irregular shapes, and as they rotate, their cross-section vary. So sometimes we see more of their area, and then they look brighter. But for Oumuamua, the brightness variation was very pronounced, because what you would expect from this type of irregular objects is just a few percent of between 10 and 20% of variation, but for Oumuamua was a factor of 10. So there is also some variation that is expected if the surface of the object is more reflected in some areas, but again, this wouldn't lead to a factor of 10 in brightness. And also the shape of the light curve indicate that the brightness variation is more likely due to its shape. This meant that Oumuamua, the shape was fairly unusual. It could be elongated, like this, with an axis ratio of at least 6:1, but it could be also disc shape. So the extreme shape has been suggested to be the result of continuous bombardment and abrasion by interstellar dust particles. Other authors argue that it could be the result of violent collisions, of tidal disruption with a larger object that came too close to because it came too close to a giant planet or to its parent star before it was ejected, or maybe due to its the shape could be due to its fractal structure. Things got even more interesting with Oumuamua when, upon close inspection, it was discovered that the object was being accelerated like a rocket. As you can see, this non-gravitational acceleration makes a noticeable difference in the trajectory. You can see it, yeah, here. So a non-gravitational acceleration was interpreted as a result of outgassing, because it's typical in comets and is caused by the mass loss that happens on the day side of the nucleus, where the ice is sublimating. For example, the impact caused by the DART mission on a near-Earth asteroid resulted in a larger than expected change in the trajectory of the asteroid because of the ice sublimation and associated mass loss that was triggered by the impact. But Oumuamua, the problem was that never show any evidence of gas or dust loss, which was another surprise because most of the planetesimals ejected from planetary systems, one would expect to be coming from beyond the snow line of their planetary system. So we would have expected a comet-like composition for these first interstellar objects. But the search for gas emission didn't find any. But it was limited because, for example, it wouldn't have been able to detect water emission at the level that would have been required for water outgassing to account for Oumuamua's non-gravitational acceleration. So the observations were limited. There are some upper limits to CN gas emission, and it is found that Oumuamua would have to be depleted by a factor of 15 relative to typical abundances in the solar system for H2, for water outgassing to account for the observed non-gravitational acceleration. Is an unusual abundance, but there are some outliers in the solar system that also have these unusual abundances for CN. And Spitzer observations also set up strict upper limits to the to CO and CO2 outgassing based on, as I said, on Spitzer observations. And Oumuamua would have to have a CO to H2O ratio of 2% and CO2 to H2O ratio of 0.2% for water outgassing to account for the observed non-gravitational accelerations. And for CO2, this upper limit is about an order of magnitude lower than what we see in the solar system. A possible explanation is that Oumuamua lost CO and CO2 prior to the observations, maybe due to multiple passes closest to its host star, or that there is a thermal lag in which outgassing begins well after perihelion. But these explanations, even though they are viable, require a fine-tuning of the sporadic outgassing through the trajectory of the object. It was also the case that Oumuamua didn't show any dust lost either. And this is particularly puzzling because if the acceleration were caused by outgassing of undetected gas species, you still have the gas dragging small dust particles along, but no dust loss was found. It has been argued that maybe there is dust loss, but only larger particles. But in this case, the outflow of dust would have been unnoticed, but there is no known mechanisms that can account for these preferentially ejections of large particles. So given all this, it was proposed that maybe the accelerations was due to radiation pressure. A crazy idea is that Oumuamua has a naturally produced fractal structure. Such a structure would provide a lot of surface area with very little mass and could also explain the unusual shape of Oumuamua. The density will need to be crazy low, about 10 to the minus 5 grams per cubic centimeter, to provide enough surface for the mass ratio to be what we would require to account for the observed acceleration. Fractals are found in many forms of nature and are thought to arise because their formation processes involve an element of stochasticity, like particle collisions in a protoplanetary disk. And here you can see an interplanetary dust particle that has a fractal structure. So some of the numerical simulations that study how planetesimals grow via dust collisions in a protoplanetary disk show that beyond the ice line, if the tiny dust particles are covered with ice and are about 0.1 microns in size, the macroscopic aggregates that form can indeed be very porous. And in fact, as the graph shows, they will have less and less density as they grow. What these studies show is that at 100 meters, about the size of Oumuamua, the planetesimals can get to ultra-low densities that are comparable to what would be required for Oumuamua to be pushed by radiation pressure. So what it was suggested is that Oumuamua could be one of those intermediate early products of the planet formation process that arise naturally from the collisional growth of dust grains. But of course, one will have to consider how such a fractal structure could have been ejected and whether it could survive in interstellar space for such long interstellar journeys. There are some studies by Flecoy and Liu that argue that such a structure could survive rotational and tide forces in interstellar space. There are other origins that have been proposed for an ultra-low density Oumuamua. Jane Liu and her group proposed that Oumuamua grew from the collection of dust particles in the coma of an active comet and then escape. And another suggestion by Sekanina is that this ultra-porous it was really an ultra-porous desiccated fragment that resulted from the disintegration of an ordinary extrasolar comet as it passed near perihelion. So there are other potential origins for Oumuamua that don't involve this ultra-porous structure. It has been suggested that it is an elongated fragment that resulted from the tidal disruption of a planet or a small body that came too close to its parent star and that it was later ejected. It has also been suggested that it's a new type of body made of molecular hydrogen, a sort of a cosmic hydrogen iceberg that originated in the coldest regions of a molecular cloud, that the temperature to keep the hydrogen on ice form is close to the ambient cosmic microwave background, making the survival very questionable. It has also been suggested that it was made of molecular nitrogen ice, so it will be like a fragment of an exopluto. But the problem in this case is to account for the inferred number density of objects. Unfortunately, we cannot confirm any of these because Oumuamua's visit was very brief and the observations were limited. So there is a wide range of wild scenarios, some of them wild, some of them reasonable, that have been invoked to understand its nature. The proposal
Amaya, just a note, we're about a minute over.
Okay. Okay.
It's
Sorry.
possible to wrap
So
soon.
let me go to talk briefly about an interesting aspect that we consider, and is we have investigated the trapping of interstellar objects during the early stages of star and planet formation, and in different environments, in a molecular cloud and in a protoplanetary disk. And what we have found is that they can get trapped in significant numbers. And this is something to keep it in mind and should be considered in future star and planet formation models, because there is an interesting question whether if they can get trapped in significant numbers, if they can act as seeds of planet formation. Let me show you briefly the other two interstellar objects that were discovered. This is Borisov. Borisov here, we have an object that looks totally like a comet. We think that this object is rich in CO, so we think it's coming almost certainly from the outermost region of its host planetary system. And this is Atlas. This is the new object that was discovered this last July. And here, the important thing to highlight is that the emission is dominated by CO2 gas. And again, this indicates that it's coming from the outer region of its planetary system. One thing that people have tried to look at is whether these objects, you can identify the parent star. It's very difficult to do so because due to stellar perturbations, you cannot really trace back the trajectory during timescales longer than a few million years, but you can trace them back to their stellar associations, and we think that this later study by Eubanks argues that Oumuamua is indeed consistent with coming from a nearby association from the Pleiades, and that Borisov is coming from an older association. For Atlas, it doesn't seem to be part of any stellar association. And the last thing that I wanted to discuss with you very briefly is that there is these studies that argue that on the one hand, we think that these objects should be pristine, and this is almost certainly the first substantial heating event since formation, but there is a new study that reports that the C2O that the ratio of carbon monoxide and carbon dioxide in Atlas and the reddening provides evidence that maybe the outer layer of the nucleus have been processed, and that this type of objects might not be pristine because of their extended exposure to galactic cosmic rays. I wanted to finish with this, is that there are many, many uncertainties regarding the size distribution, regarding the number density, how many interlopers are iceless and weirdly shaped like Oumuamua versus how many are rich in ice. And we don't know much about their composition. because we only have observed three objects, right? So with Vera Rubin, there is going to be a revolution in this regard, because we expect that the number of interstellar object detections will be between a dozen and maybe 100 a year. And this will allow us to learn much more about the population and learn if, for example, if it can be the population can be related to free floating planets. Here in this figure from Jewitt, we saw that how the two populations might be connected in spite of the many orders of difference of magnitude in mass, and this is something that we will be able to explore once we know more about the population of objects. And that's it. I wanted to finish it here. Sorry for being over time.
Thank you, Amaya. So as the next speaker, if you could come up and set up, maybe we'll take one very quick question.
Hi, Amaya. I'm Takasumi.
Hi.
Yeah, it's been a while. So nice talk. I had a questions. So this population of the interstellar planetesimal, they already had enough time to be uniformly distributed in the galaxy, so that we can measure the average number by the observation by the Rubin, or still locally we can see only the local population.
I think this is what we need to learn with Vera Rubin, right? We need to learn about the distribution. We need to, like, there is the suggestion that Oumuamua and Borisov come from the thin disk, and Atlas will come is consistent with coming from the thick disk. We don't know yet. But for certainly the ones that are coming from nearby associations, they wouldn't be isotropically distributed, right? So if Oumuamua is coming from the Pleiades, you wouldn't expect the objects ejected from this association to be distributed isotropically. So, but this is something that is still one of the things that we need to learn from the Vera Rubin Observatory, because we only know three objects, so it's very difficult to say anything in terms of a population.
Great. Let's give Amaya one last round of applause. Nice.
Thank you.